Okay, Journal Club is officially in session. So today we're going to talk a little bit about Attention is All You Need, the kind of seminal work on transformers. The whole idea is that we started by using these recurrent. Well, I mean, not started. Obviously, there's a massive history to natural language processing, but we're using recurrent neural networks to begin this era. And then people started to say, okay, let's use this thing called attention to improve them. And then these authors here decided that they would just ditch everything but attention. And obviously that works well because we see pretty much every important paper in the last, not every, but many, many important papers in the last year or 2 years. Well, yeah, the last year or so. Well, what date is this? 2017. So yeah, it's fair to say a lot of important work in the past 3 years has been done based on this one paper because it's super important. One thing to note is that there's some really, really good instances of illustrations of transformers. For instance, let me look this one up. It's just called the Illustrated Transformer. Let's see. So it just as a kind of companion to this paper, it talks about self-attention. It talks about the encoder-decoder setup. It talks about positional encoding. So it's pretty useful for visualizing what is happening in these networks. That's just a good tip for a place to look, a good resource. But anyways, if anyone has questions, feel free to jump in because I think it's great to, address things because if you have a question about the paper, then there are probably a ton of other people who do as well. But so they talk in the introduction about how recurrent models have started using attention and it improves their performance, but there's still this problem of recurrent models are sequential, so they kind of take in they take in input one at a time and they process it in a manner that is step 1, step 2, step 3, step 4. In contrast, transformers can be used in parallel so that it's okay, we're going to do 50 steps all at once instead of saying, here's step 1, here's step 2, here's step 3, here's step 4. In fact, let me find a good... Yeah, here we go. I don't want memorization. I'll just go to images. I'm sure there are some good ones. In fact, I actually have a slide that I did a long while back. Let me find that. Maybe it'll let me search all of them. Okay. Okay, so here's a good way of kind of visualizing the difference. A recurrent neural network is going to start with the cat, is going to do some processing, go on to was, and then go on to orange. And it's all kind of a linear serial process. In contrast, you have the transformer, which is not only able to attend to the whole sentence at once, but also is able to be run in parallel using matrix transformation, using matrix algebra, which is another thing that they talk about in this paper. There's this idea out there of it's not necessarily that the best architecture always wins. It's also that the architecture, and I can't remember who said this, there was a paper about it, it's called the hardware lottery or something, but the architecture that is best suited for hardware will also have huge advantages, even if it's not necessarily intrinsically better. The fact that you can make things run in parallel on a GPU with a transformer is probably a large part of why they have completely overrun recurrent neural networks and kind of made them not necessarily obsolete. They're useful for some tasks, but much less prevalent in the literature today. So let's dig into, after talking about how they're, again, these kind of parallelizable, that's a hard word to say, parallelizable system. Let's talk a little bit about what they actually look like. So we talked a little bit about feed-forward networks. Now we're going to talk about something that builds on that called attention. So you have linear, just means it's like a dense feed-forward neural network. So it's like two layers of just a feed-forward, the default kind of basic neural network. To get the attention out of them, let's see if they have a good, no, I don't know if they do, but I'm sure the illustrated transformer will.
Ren, are you sharing your screen? Because I'm not seeing it.
Oh shoot, I didn't realize I wasn't sharing my screen. I am recording it, but I am not sharing it. Thank you so much. Okay. So now you can see it, I hope. So the big thing with this paper is, again, that everything is parallelizable and that you can attend to multiple things at once instead of going one step at a time and kind of keeping things in memory. So let me find, this is a good example. So what really differentiates transformers from recurrent neural networks and convolutional neural networks is that as you try to attend to things like the animal did cross all of these different words in this sentence, instead of making it so you have to step through each word, it's basically saying we're just going to input the whole sentence and we're going to let certain words be influenced, their representation be influenced by other words, and then we're going to process that with neural networks. So self-attention in detail. So you can think of it as a whole bunch of tiny little neural networks, each operating on each word. So you start with an embedding, which is basically like taking a word and turning it into a bunch of numbers, a vector, and you kind of learn how to take thinking and turn it into a vector by learning a set of weights that are, well, that's kind of into the weeds. But anyways, you take this word thinking, you turn it into a vector, you then have queries, keys, and values. And the matrix algebra is not too complicated, but I'm not really going to get into it. But the basic idea is you have queries and keys, which are used to compare, which are used to basically weight the values. So for the word thinking, you have a certain value that represents thinking. You then have the queries and keys, which then say, okay, so we also have the word machines. How well do the queries and keys produced from thinking and machines match? And based on how well they matched, they'll literally just combine these representations relative to how well matched the queries and keys were. So this at first this doesn't seem super powerful or super interesting, but when you realize that you can take a whole sentence and say, cat is going to be compared to the itself, was, and orange, you can take that and you can say, okay, we're going to change the representation of cat to include some of the, some of was, and some of orange based on what these neural networks decide. So you can think of attention as basically saying, we're going to take every word in the sentence up to a certain point, because we don't want to have the cat be able to attend to words after it, because then it can cheat when it's guessing the next word. That's another thing to mention. The goal of most transformers is, well, the goal of things like GPT-2 at least, is to guess the next word. And to do that, they take in the input, the cat, and they compare the and cat. And then on the next run, after predicting, something like was, they take in the cat was, and they look at every single word following it and the word itself, and they weight the representations of those and combine them together based on the output of these query and key vectors. And the way that they do that is they basically use cosine similarity to say like, okay, query is really similar to key, so the neural network has learned that these are two important things to combine together. So we're gonna combine their representations to some extent and then feed it through another neural network. And it does this with multiple heads. Let's see if I can find an example of that. So instead of just doing that once at every layer, they do that like 8 times at every layer, so that the neural networks can attend to different properties of the sentence. If that makes sense. If anyone has questions, again, feel free to stop me or jump in, but I'll just continue rolling along on this paper if there aren't any.
Ty, I came in a little late. Are we doing the attention is all you need paper today?
Yep, that's the one we're doing right now. Yep.
Okay.
So getting back into the paper itself, so I kind of had to veer off before I could talk about the model architecture. But now that we kind of have an idea of what attention is, you have the embedding, again, just transforming a word into a vector. You have, and we'll talk about positional encoding in like half a second. You have this multi-headed attention where it's like, okay, how do these words each relate to each other word within the sentence? And how can we combine their representations together? Then you have a residual connection. Residual connections are super important for transformers, and they're also in many neural networks super important for convolutional neural networks. They're super important for some even dense feed forward neural networks. But the basic idea of a residual is that instead of saying, okay, we're just going to process this layer by layer, you also add the output of a layer to the layer after it. And there are some reasons that this is useful. It kind of allows the gradient to flow and kind of like skip over chunks. So if you get an initial, this is my intuition, it may be outdated. There could be some disagreements. It could be debatable. But you can go through all of these layers, and instead of the gradient having to pass through, well, actually, let me back up a little bit on that. You could go through these layers, and they're all randomly initialized. But if the random initialization is bad, you can kind of just skip over that layer and just add on to a whole bunch of zeros, which may explain to some extent why these residual connections are easier to use for the neural network than just having it go straight through all of the layers. So it's like you start with your input, you process it a little bit. Let's say that you come to a neural network within, let's say you come to some layers within the neural network that are not useful because of their initialization. You can literally just have the gradient set those to 0 and then jump over it with a residual connection. That's at least some intuition as to why residuals seem to work well in a number of different architectures. But again, residual just means add the input to the output of a layer. So you have that. Add and norm, again, the add is just the residual. The norm is like layer norm. So that just kind of takes the output and then makes it so that it's well behaved. You could talk about network like batch normalization, layer normalization for hours, and there's some controversy as to like how it works and why it works. But the basic idea with any kind of normalization is to make it so everything sums to a certain value and so that the output doesn't like explode or anything like that. So then after you have that add and norm, you have another residual, and in between that residual you have the feed forward, basic neural network. But again, multi-head attention is just made up of 3 feed forward, each head is made up of 3 feed forward neural networks that all work together to do attention. And then there's this idea of an encoder and a decoder, which basically is just that you take the text and you take it down to a certain vector and then in the decoder you can then output as many words as you need. It kind of gives an output of a whole bunch of probabilities of the whole vocabulary that it knows. So it'll give the probability of, sandwich. Well, I mean, unless it's like a compound word, but it would give out the probabilities of cat, dog, every word that it has in its vocabulary is going to say how likely it is that the next word or whatever task it's doing, it's going to say how likely that word is to be the correct word coming out of it. That's what softmax does for us. Any pressing questions so far? Because I'm happy to back up and explain stuff earlier on that I talked about, because I know this is kind of a lot all at once. Okay, I'll keep going then. So you have this encoder, this decoder. Let's talk a little bit about positional encoding. So what I've described so far does not take into account in any way the order of the words that you put in, which is a problem because obviously when we read in a way that is, well, and obviously it's, conducive to know that sentences have an order to the words. You couldn't say, the dog was chonky, and mix it up and get the same understanding of it. The was chonky dog, was chonky the dog. These all mean different things or nothing at all, depending on what order the words are put in. So we need to have some way of telling the neural network what order the words are in. And the way that they do that is they say, we're just going to add a positional encoding to the input embedding. So they're literally just saying, okay, we're going to say, we're going to have our word embeddings and we're just going to do plus some positional encoding. And there are a lot of different ways that you can do positional encoding. Let me see if I think they have an illustration of it here somewhere. Maybe. Oh, perfect. Let's see. Or maybe not, but I'm sure. Let's see. Okay, yeah, this is one. So they encode the position by using a whole bunch of different sign embeddings. Let me see if there's a yeah, so they use the sign function. That's what this is kind of illustrating, and they basically just say we're going to put the position that it's at in a whole bunch of different sign functions with different multipliers within the function. So it's like you can stretch out a sine wave or you can squeeze it, and they just do that a ton of different times and run the position into that. And then they just add it to the word embedding, which is kind of a strange, when you think about it, it's like, why would that work when they want to concatenate it so that it's like, making the vector, distinct in that way. But apparently just adding it seems to work well, because I think that's something that is still pretty common. Let's see. Let's see. Do I have water here? Yes, I do have water. My throat is getting dry. If I drink enough water while I talk about this paper, this becomes an ASMR video, and that's a plus, I think. Let's see. Oh, it looks like Cobalt Owl is typing, so I'll wait a little bit to see their message. Yeah, so I can go into, I feel like there should be a better illustration than what I've shown so far, but the idea of attention is that you take each word in the sentence and you take each other word in the sentence, and then you say, based on these learned neural networks, which learn which words are important to each other, we're going to say, in fact, let's see. Yeah, I kind of like this illustration. So we're going to say, if we're at the word it, we're comparing it to every other word in the sentence. As a caveat, if the word is in front of it, like if the word is after it, they're going to mask it. They're basically going to say, don't pay attention to this one. But we're going to take the word it, and the neural networks are going to say, it relates to because, however much based on the query and key values, which are just vectors that are then compared using cosine similarity. So it's basically just saying how important is the word it to because, and then it's going to alter the representation that it has by adding part of the because representation, which is just kind of mind-blowing in a way, because it's like we're literally kind of mixing together these representations of these words, certain amounts depending on how not just related they are, but how like syntactically related, or how like semantically related they are. And as you get like 50, I don't know, many layers of that and many nodes of that, it starts to learn to associate these words in really important ways. And one way I could maybe explain it is writing out the code or showing you the code, but I'll wait until you've finished typing. Oh, how does that work outside of NLP? Well, that's a good question, because I actually have a paper coming out soon on how and the probably more interesting case is using like image processing, but I'll really quickly go over how this relates to material science property prediction. So basically what you can do is you can take any set of you can take any representation, like a sentence or a in the image processing domain, you could say, we're going to take this picture and we're going to say that every pixel or every group of pixels is like a word, and we're going to treat the whole thing like a sentence. So it always kind of comes back to this analogy of like a sentence is the whole representation, and then it's broken down into words or even subwords or even letters. So with material science, you can say every atom is a word within the sentence of a crystal structure. And when you do that, you can then treat it just like you would a sentence and say, okay, which atoms are important for other atoms, and how do they and how can we create interactions between them that tell us certain things about that crystal structure. The probably more interesting example for everyone here is with image processing, where you can say, okay, we're going to run a convolutional neural network on patches of the image. This is basically what the vision transformer does. We're going to run a convolutional neural network. It's going to represent a whole bunch of patches of the image, and then we're going to combine those patches and have them attend to each other, and then use those representations after doing a ton of attention and a ton of different layers with a ton of processing in between. We're going to take that and we're going to output like a classification. Or in the case of Clip, what's going on is you have that vision transformer, which takes a convolutional neural network and runs a whole bunch of patches through it to create, sub-units of the whole image and then compare them together. With Clip, you're just doing that for an image, and then you're outputting a vector, and then you're doing the exact same thing for text, and you're outputting a vector, and then you're comparing those vectors also using cosine similarity, like within attention, and you're saying like, whoa, we can use this to teach the neural network to say, okay, this description is pretty similar to this image, which was previously broken down into patches. And so a lot of the trick here is using cosine similarity to be able to kind of match different vectors and say how similar they are, and in the case of attention, to use that to weight the representation of the words together and kind of like sum them all based on a weighting. So as an example, again, you have it and you have the representation that comes out of one layer of the transformer, and then you have it and you combine it with these representations that have all changed together to be different weightings of each other. Because the basis of attention really is an each to each comparison, where you have all of your words compared to all of your other words, or all of whatever representation compared to all the other ones, and then based on that comparison, weighting the representation by adding in parts of the other by adding in the other representations of the other parts, but weighting that to some extent. And so what we find when using transformers is that they're really, really good at learning these long distance dependencies. So they can say like, okay, the word. So like while a convolutional neural network would not have as easy a time of saying like, okay, this patch of an image is related to a patch of an image like way across the screen. Like let me pull up an image real quick. So a convolutional neural network would be like, okay, oh, that's not an image, that's a video. That's also a video. Fun. Yeah. So what the hell? Why do I have so many videos? Okay, let me scroll. Okay, there we go. Finally. So while a convolutional neural network might have a hard time relating this patch of an image to this patch of an image, because it's just kind of doing filters that get progressively more precise, a transformer is built so that it is definitely comparing this patch of an image to this patch of an image, no matter what. So it has this kind of unique nature that makes it so that even if something's far away, it's still using attention to relate this thing to this thing in the image. And that's a lot of what makes them so important, is that they can powerfully model long distance dependencies, with the long distance dependency just being like a far away subunit of the representation that's important for a far away other subunit representation. So yeah, those are both really good questions. If anyone has more, or if there are follow-ups, totally feel free to ask. But yeah, I'm gonna keep making this an ASMR video, so I hope everyone appreciates that. Water. Let's see. Okay, now I'm trying to think of other important points in the paper. Oh, okay. I'll wait for Miles. Oh, okay, that's good to know. Yeah, like whenever I'm on a Zoom meeting or like a Zoom call, I'm always like, how much of my drinking can people hear? And it's like, who knows? Who can really say? But that's good to know. Okay, so we have attention, and we do attention with multiple heads, so that the neural network can attend to different concepts going on and different things going on. Let's see, what else is there that's important? Positional encodings, embeddings and softmax. Why self-attention? We kind of talked about that. So the first thing is it's computationally very conducive to like running quickly and running well. Let's see, what else is there? they talk about path length, which is just this idea of long-range dependencies where you have something important that's far away from something else in their representation, and they're able to take advantage of those, while other neural networks have a hard time with that. So that's a good thing to know. They use Atom. They have some kind of tricks that they use with optimizers and transformers, because transformers are kind of notorious for being hard to optimize. It's very fortunate that they were able to figure out that altering the learning rate this way works, because otherwise we would not have things like GPT-2. So that's good. They use Dropout so that it doesn't overfit. Dropout's kind of fun. If people don't know what Dropout is, it's basically you run your neural network during training and you set some of the outputs of your neurons to just be 0, which is kind of cool, because it's like, why would that be useful at all? And the answer is this is another thing where I'm sure there's some debate, and I am probably a little bit outdated on the literature's take on this, but you could probably argue like Dropout is useful because it makes it so that it doesn't rely on just one neuron too much and like memorize things. So it's a regularization that makes it so that you're less likely to overfit and memorize words, and more likely to get like, so-called understanding out of the network instead of just memorization. So they use a lot of this work is often benchmarked with machine translation, where it's like, can we go from French to English? That's just one thing that is, at least in the circles that I run in, less thought about compared to generation nowadays. But I mean, obviously, machine translation is super important and super good. One cool thing that they did was they kind of went through a whole bunch of different permutations of what the parameters of the model might look like. So like how many feed-forward networks, or no, what the dimensionality of the feed-forward networks could be, which is just like how many neurons there are, basically. I think that might be how many layers or something, and might be number of heads or some. I don't know. I haven't read this table very closely, but let's see, what else is there that's interesting in this paper? Yeah, I mean, the paper is just super important because transformers are just super important and super cool. You might read in the paper, if you look into it, that they're autoregressive. That just means that when they take an input, they then output something, and then they take the output and then create and then use that as their new input. So basically, the idea is just like it can model sequences that are as long as you need them to be. So instead of it being like the dog, and that maps onto another two-word sentences like the cat, they can say the dog, and they can say the cat, that dog is here. Just saying, like, you can take a variable number of words as your output before stopping, instead of having to go from 2 words to 2 other words, which would obviously not be ideal. Let's see. This is kind of what attention looks like when you write it out as matrices. You have the query, the key, and the value. You do softmax over the query and key. So so basically, this is another way of thinking about it. You have the query and key, which tell you how important these words for each other. You multiply them and transpose the key. We can ignore this. This is just to make it so things don't explode with like the gradient getting too big or the outputs getting too big. So you have the query and the key, and you transpose the key and you matrix multiply it with the query. And what that does is it creates a matrix that they then do softmax on. So all of the values in the matrix are going to sum up to 1. or all of the rows within the matrix are going to sum up to 1. And then that means you can basically say, okay, we're going to multiply that by the values. And this is the magic part where it's like this query and key are going to say, okay, this is how important each word is to each other word, and it's going to be bound from 0 to 1, so it all sums up to 1. So you end up with a representation, and I think this is just so cool, you end up with a representation that's just summing up all of the different words with respect to how important they are to each other. So again, you have the, and the is really going to be important for street. And so you're just going to say, okay, we'll add a whole bunch of the street representation into the, and less so with the other representations over here that will be summed into it. Yeah. Any pressing questions or comments or anything about transformers? Cool. Trying to think of other things about this paper that are. I think they do. So one interesting tidbit that I hadn't noticed until reading this more recently, they have their models and they use a model that is obtained by averaging the last 5 checkpoints of their models. So like they train a model and they've got 5 checkpoints, and every 10 minutes they're saving a checkpoint, and then they just take the average of that. And it's similar to what people do with GANs a lot lately, where like you want to take the average of a number of different models as training goes by, because it improves quality a lot. And the reason it improves quality a lot is probably like there will be some weird peculiarities to the weights of a specific checkpoint of a specific model during training. And you can average those out so you get to like a better, kind of more global minimum when you do that. Just something to think about. It's something I've wanted to implement into my big sleep systems and Aleph, because it's like you could just average the kind of latent vectors and maybe get a better latent vector overall by saying, we're just going to keep a running average of all of the previous ones. Okay, that's a lot of talking. Trying to think if there's anything else of note. Like it's such a great paper. It's also not that long, which is something that I really, really enjoy in a paper. Not feeling like you have to go through everything for 10 years. And they have an appendix which visualizes some attention, which is really cool. Could averaging the DALI encoder model in BQGAN help with the left? I think that you would have a hard time averaging the encoder model and the BQGAN together, if that's what you mean by it, because they're different. They have a different number of parameters. But I think that averaging the input to them, so like averaging the latent space input, definitely could help. Yeah, I think in general, taking an average of neural networks is a very helpful thing to do, because then, like, again, you just reach a more global optimum a lot of the time, like a lower kind of place in the lost landscape. I need to check and make sure while people are talking if I have enough space to save this. I have 12 gigabytes. I should be good. It should only be like half a gig, ultimately. But yeah, I do think like you could maybe do, I don't know, maybe they already did this with the BQGAN, but you could maybe find some checkpoints and say like, okay, we're gonna, since they're the same type of architecture and they have the same number of parameters, we'll average those weights. That's definitely a good idea. Another thing, this is totally a tangent, but another thing to try is fine-tuning the different things that we have. I don't know, maybe it would be hard to find enough descriptions and images to pair together, but it'd be fun to see if you could do it like a specifically, like, I don't know, Pokemon clip or something like that, and then do gradient descent with it. How practical do you think it is for humans to manually interpret and adjust attention vectors for more carefully guided results in popular transformer architectures? In something like GPT-2, to manually interpret it and adjust attention, it would take like a year. So, but this is a good point, because there are ways that you can adjust the network using like reinforcement learning. So like when you get an output from GPT-2, you can have a person be like, oh, this is super bad, change the weights. And you're not like manually going in and tweaking it, but you are telling it based on human input, like, hey, I don't like this response for whatever reason, so update the weights to get this response less often. I think, let me see if I can find it. Yeah, here we go. Here, oh yeah, so this is exactly that kind of thing. I'll post the link in the chat real quick. But OpenAI was like, why not fine-tune these models kind of by having humans look at specific outputs and be like, okay, this is bad, this is good. And I mean, it's kind of amazing, because 5K or even 60K is not a ton compared to how huge these are. I'm gonna remove, yeah, okay. Yeah, so that's definitely there's definitely this thing where it's like we want to be able to put humans more in the loop, and I think it's hard because these models are so massive that it's like you could take forever looking through them and trying to fix things. But there are ways of putting people in the loop that are really kind of interesting and pretty effective, it seems like, based on that blog post that I read a very long time ago. Does anyone have, I'm thinking maybe we want to read the clip paper next, but I'm also very much open to reading other papers. Does anyone have any input on papers that would be fun to look into? Yeah, and it kind of follows from like talking about transformers, because like I said, CLIP is basically a transformer that encodes text and a transformer / convolutional neural network that encodes images, you know. So it's like it's definitely built into how CLIP works, you know. Cool. I'll pull that up right now. I'll find the CLIP paper. I'm trying to think if there's anything. I'll be honest, and I think this is hilarious. I haven't read the paper that closely. You would think that having based a lot of my previous like month, well, probably like 3 months around this one network, I would look closely at the paper, but I'll do a little look through right now to see if I think there's anything. Yeah, I mean, you got the text and image encoder from a high level, which are both, you know, transformers, unless you're using the ResNet version, but like, you know, whatever. They'll talk about, yeah, I think this will be good. Yeah, that should be good. I don't think, wow, an amazingly long paper in comparison. Holy cow. Let's see, what else is there in here? Yeah, I think we can go here next. I think that'll be good. Huh. Bias. Oh, I'm glad they talk about bias. That's good. What else do they talk about? Limitations. Yeah. Data overlap. There's it to human. Yeah, this will be good. I think that'll be fun. Okay, and let me post the link. Oh, where'd that go? Okay. Oh, I closed the wrong one, didn't I? Oh. Oh yeah, that's a really good question. And there's a very good paper about this. I'll have to find it. Yeah, so the attention parts of a network are actually quite good at doing other tasks. So I gotta find this paper because it's super relevant to this question. But yeah, you can take a neural network like GPT-2 and you can take its attention and you can train just a very little part of GPT-2 to do a totally different task. So let me see if I can find it. I'll go to Twitter because I think I saw it there. Transformer, Universal. I think this is it, probably. We investigate the capability of a transformer pre-trained on natural language to generalize to other modalities with minimal fine-tuning. Yeah, this is it. So the answer is it transfers like surprisingly well to other domains and other modalities. I can't believe I need to read this paper as well because it's pretty damn cool. But it's like they take GPT-2 and they use barely any of the parameters. Like they don't change much of GPT-2 at all, but they end up with a GPT-2 that can do, other tasks that are very different from text natural language processing. So pretty cool stuff, I think. Yeah. Oh, it looks like Bosch Ray has posted some. Oh, these rock. I love these. Okay. So we've got like 7 minutes. I'm thinking I'll just hang out here for a little bit. If anyone has questions, and especially if anyone has like, just if anyone has questions, this is like open time for any question because I think that's most of the stuff I wanted to go over with that specific paper. I like how there's some like, elasticity to the window. Kind of cool. Oh. have like a reflex that makes me open Twitter whenever I'm... Oh, okay, here we go. So something I've been wondering, could the Aleph notebook be set up to train for a really long time on a single text prompt, like over multiple days, with saving and reloading checkpoints, and then have it generate a new image with that training? So set up to train, so train it for like days and save and checkpoint, and generate a new image with that training. So like doing really prolonged training and then loading up and have it generate a new image with the... Yeah, I mean, you could, it would be possible, I think. You just train for like many days, and I also think it would be interesting to would it produce much better results? Yeah, I don't know. It's weird because like I found that training, especially with the latest patron only like Aleph, I found that training for a really long time kind of helps, but I think that training for a really long time and then, like people have mentioned and like I've been wanting to do, I don't know that training for a day will make it produce much better results. But I do think that training it for a day and then taking like an average, well, maybe not even that, but I don't know how long it keeps improving. I think it generally keeps improving for like at least an hour, but there comes a certain point where it's like not really descending into the valleys and the so I think that the answer is I'm not sure. It's definitely something to try. It would probably also be good if you were to try training for like a day or 2 days or something. It'd be good to figure out if like making the learning rate decay at a certain rate. I think it's decaying already, but making it decay slower might end up getting you like a much better image compared to if you don't decay it. Because there's always this balance between like how quickly do I want to find a good image and how broad do I want my search to be over possible images. But I think that I think maybe it would do better results given a ton of time training. I'm not certain. With the decay set at what it is right now, I think you'd get to like 0 learning rate pretty quickly, or something equivalent to a 0 learning rate. So you would get diminishing returns, but you could do something like have it slowly decay the learning rate, and then have it kind of like go back and start. Like there's this thing called cosine annealing with warm restarts, where you just kind of like train the network and then decay it the learning rate slowly until it gets to a good place, and then you kind of like restart training and do it all over again, and you do that a couple of times. I think that would be promising for producing good results over a very long period of time. So it would be, will it let me link directly to this? I don't know, but yeah, this would be something to try if you're going to train it for like a couple of days. But I'm not sure exactly what would happen. That's a good question. Well, we've got about 1 minute left. I might hang around a little bit. I don't know what I'll do. I don't know. I have a ton of work, but I don't want to do it, so I'll probably hang around in the chat in the voice chat for a little bit. But thanks everybody for coming to the meeting. I appreciate it. And I think it'll be. Oh, and I guess I'll post this recording. I'll try to make sure not to forget. In fact, I'll do that right now while I wait for people to